Hello, this is Mr. Gumler with the 7.5 application lesson. Now, we've come to a point in our chapter where we have learned a lot of new tools, and now is the day we're going to put those tools into practice. This application lesson is going to contain application of just finding similarity between triangles, but it's also going to be used in several new theorems that we can unpack using, again, the power of similarity. Let's jump right into our first example with some application of similarity. Let's consider the diagram below. We actually have three triangles that you can envision with this diagram. We have triangle ABC, the entire triangle, but with the segment BD drawn into it, it cuts it into two smaller triangles, ABD and CBD. What's interesting about this diagram is because we are given BAD and CBD, those two angles, angle BAD and angle CBD, are equal in measure, we actually have some similar triangles. Take a look what's happening. There are two triangles in this diagram in which share angle C. And because they share angle C, that means we do have two angles of one triangle equal to two angles of another. But which triangles are these? Let's go ahead and unpack a similarity statement. Notice that the entire triangle ABC contains the equal angle A and the angle C, and there's a smaller triangle, triangle CBD, that also contains the equal angle CBD and the shared angle C, which means we have a pair of triangles that are in fact similar. Let's go ahead and unpack what that similarity looks like. It would be ABC, the entire triangle, is similar then to triangle BDC. And because of that similarity, there's actually some unique proportions that come out of that. One of the unique proportions that come out of that relates to the side BC. Here's why. Look at the segment BC. Not only is it a part of the entire triangle ABC, but it's also part of its smaller similar triangle CBD, which means there's a unique proportion that we can pull out of this. Notice that from my similarity statement, I can actually find that unique proportion by matching up my corresponding parts. So I'm going to choose the entire side length AC. Notice that AC of my larger triangle actually corresponds with BC of my smaller triangle. And if I ratio that with then BC of my larger triangle, it then corresponds with the segment DC of my smaller triangle. And so this is the proportion that is actually a kind of a unique proportion, because take a look what's happening there. There's only three values in that proportion. BC is used twice. And because of that, we can then do some interesting computation to find or solve for that missing value of BC, needing only two values, not three, right? Usually a proportion with four variables, we would need three given to us. In this case, we'd only need two given to us. So let's dive into an example of taking this triangle with us and taking this proportion with us in the next slide. So now let's do this with numbers. Again, that proportion was that we had AC over BC, right? If we find those two similar triangles again, right, because they share this angle C, AC to BC is equal to BC to DC. Okay, so the entire side length of our large to the side BC is then equal to the ratio of BC to the side CD. Well, notice what they give us. We are given the length of BC and we're given the length of DC. We're looking for the side length of AC. So let's plug in what we know. So AC is what we're looking for. BC is 12. The 12 goes in two places because I'm using BC twice, and then DC as 9. So now what we can do is cross multiply and solve. So I'm going to do 9 times AC. 12 times 12 is 144. Divide both sides by 9. We get AC to be a length of 16. And there we have it. Okay, using that unique similarity found in this diagram, where we find there's kind of this part-whole similarity, right, where part of the whole thing is similar to itself. So kind of interesting things going on, especially with this example. Now let's consider this diagram. Okay, let's consider this diagram. We are given a triangle ABC such that it is a right triangle at angle B. Now with segment BD drawn in there, notice that it does cut the larger triangle into two smaller triangles, ADB and CDB. But that segment BD is a special segment. It's considered an altitude, right? It's actually drawn from point B perpendicular to the side AC. And because of that, it forms a right angle. The two smaller triangles that the segment BD is cutting the larger triangle into are also right triangles, right? If you take a look, CDB is a right triangle with angle at the vertex D, and ADB is a right triangle with the right angle at vertex D. What that means is we actually have three triangles in which they are all similar to each other. Yeah, there are three similar triangles here. Why? Well, because the larger triangle, the largest triangle, ABC, and the smallest triangle here, ADB, they share this angle A, which means there are two angles of that triangle equal to two angles of another. They're similar by angle-angle similarity. And again, the largest triangle, ABC, shares angle C with kind of the medium-sized triangle, CDB, which means two angles of that triangle are similar to two angles of that one. And then through the third angle theorem, we can show that these angles here are also equal to each other by third angle theorem, and so that means the smallest triangle, ADB, is similar to the middle triangle there, CDB. And because of that, we have three similar triangles, which means I can write out a unique extended similarity statement. So let's go ahead and do that. So I'm going to start with the entire triangle, ABC, and I'm going to then go to the middle triangle, the middle one, sorry, the medium-sized one, and ratio with that one. So I have, let's see, ABC would then be similar to BDC, which then is similar to the smallest triangle. And let's make sure I match my corresponding parts. That would be ADB. And there we have it. So all three triangles there are in fact similar. Well, what that means is we can unpack some unique proportions from this. Let me go ahead and show you kind of some of the unique proportions that come out of this, similar to what we saw with that previous part-whole similarity diagram on the last slide. So what I can do is I'm going to be ratioing the hypotenuse of the entire right triangle, AC. That's kind of the link to form these special relationships. Let me go ahead and unpack the special proportions here for us. So as it turns out, AC, if we were to choose AC, the hypotenuse, it is then, I can ratio it to either the middle, the medium-sized triangle, or the smaller triangle there. I'm going to stick with the middle triangle, the medium-sized triangle right now, but I can also set up a second proportion where it's ratioed with a smaller triangle. So let me go ahead and unpack this special proportion. AC is then ratioed to BC, right? If I chose a side of my first triangle, it's then corresponding to the side of a second triangle, which is BC. As it turns out, BC is the leg of that right triangle, but not only is it the leg, it's the hypotenuse of the middle triangle, the medium-sized triangle, which means if I set up a second ratio, I form a ratio of BC, okay, of my larger triangle, BC, to the smaller triangle, which would then be CD. So notice what's happening in this proportion. BC is used twice. And because of that, again, we find this proportion where we only need two values to help solve this proportion because there are only three variables. Now, there is a second proportion we can form. Okay, there's a second proportion we can form. Again, using our hypotenuse AC. But this case, let's ratio it with the smallest triangle here, ADB, and we'll find again something special as we unpack this one. So if I ratio AC to the smaller one, AC then corresponds to AB, which is the leg of that right triangle, but that leg is also the hypotenuse of the smaller triangle, which means the second ratio I'd find would be, again, hypotenuse to the leg of the smaller one, so it would be AB to AD. Okay, and because of that, right, because of this, again, special similarity, look at the second proportion. There again is a repeat of a value. AB is in there twice. So we'd only need two values to then solve that. So let's take these two proportions with us as we then move into, well, let's throw some numbers in here and see what happens. And we're going to take these two proportions to help us solve for some missing components within this part-whole similarity that we see as we're cutting this right triangle into two smaller similar right triangles. Okay, so now with numbers. So what were those two proportions that we brought along with it, or we found on the last slide? Let me go ahead and give those to you again. So it would be AC ratioed to BC is equal to BC over CD. That's the first ratio, or first proportion. Second proportion was again the hypotenuse, the entire hypotenuse, AC, to AB, the smallest triangle, is then equal to AB over AD. Now, let's take a look at what we are given. We are given the lengths of AB and BC. What we're going to do is find the length of AC using these two proportions. Now, to help us out algebraically, let's go ahead, let's just call the entire side length of AC, let's call that the variable y, and let's call then this length of our segment here, CD, a length of x, which then means for the length of AD, we can simply express it in terms of those variables as y minus x. And then with these variables that we have produced here and these proportions we have found, we can then solve for our missing value of our length of AC. So let's go ahead, plug in what we know, and let's go ahead and solve. So let's start with our first proportion here with AC to BC. So I know AC I've let to be the variable y. BC is given to us as a length of 4. And CD we represented with x. And you're probably thinking, oh no, we have two variables in this one equation, which means we can't necessarily solve for one of those directly right now. And you'll see that it will help here in just a second. This proportion will help us. I'm going to go ahead and cross multiply this to get xy is equal to 16. Now we'll see the use of this this equation here in just a second, because what I'm going to do next is go to my second proportion and plug in those respective values. So AC, AC, we have then let that be our y value again. AB is given to us as a length of 3. And this time AD, remember, we've represented as those two variables, y minus x, right? The whole thing minus the x measurement, which gives us then the length of AD there. Let's then cross multiply here. As I cross multiply, y times y gives me y squared. Y times x gives me a minus yx, and then 3 times 3 is equal to 9. So notice now, again, oh no, I have a two-variable equation. I can't solve that directly. However, using both of these equations together, I can solve it. Take a look. I know that x times y is 16. So then take a look at what's going on in the second equation. I have y squared minus x times y equals 9. I can replace that x times y with its corresponding counterpart, 16. So I get then y squared minus 16 is equal to 9. I can add then the 16 to both sides, getting me as 25, and then take the square root of both sides, and it's the principal square root would just apply because we know all values in our segment are positive, which then means y is equal to 5. Now, you may be wondering, hold on, what did we just do there? We took the two lengths of a right triangle, the two legs of a right triangle, and we found the hypotenuse. If you're thinking what I'm thinking, you're on the right track. We actually just discovered something related to, that's right, the Pythagorean theorem. Okay, there is, with the proportions that we just discovered with that similarity, there is essentially the underneath ground support for the Pythagorean theorem. This is actually what we're going to see as we move into chapter 8. How we're going to prove the Pythagorean theorem is with similarity. So there we have it, right? With this part-whole similarity with our right triangles, leads us into the foundation of, yes, the Pythagorean theorem. Okay, let's move on to some other theorems that we can actually prove with similarity. This next one's called the triangle medians theorem. Let me explain what a median is. A median is a segment that is then that connects from the vertex of a triangle to the midpoint of the opposite side. So in our diagram below, there's actually two medians going on in that diagram. There's the median AE and the median CD. E is the midpoint of side BC and D is the midpoint of side AB. And if I connect the opposite vertex to that midpoint, we form that special segment that we call the median. Well, as it turns out, something kind of unique happens when you draw in two medians. Their point of intersection is actually 2/3 of the entire length of that median. So in the diagram, what I'm going to ask you to prove, specifically for one of our medians, you can show it for the other as well, but just showing it for one, then we can extrapolate to say, well, it then must be true for the others, that we're going to prove that AF is actually then equal to 2/3 of the entire median AE. Now, I'm going to let you do this proof on your own. However, I do give you several hints on the worksheet, and I'm going to give you those hints here now in the slides here. So the very first hint you're going to do is this. You're going to connect point D to point E. Okay, that's your very first thing you want to do. Connect point D to point E. We're connecting the midpoints D and E. Well, you notice what we're doing there? We're connecting midpoints. So your very first, so once you've connected D to E, your next hint is this. What type of segment, right? What type of segment is the segment DE? You should recognize what kind of segment that is because we have a theorem that relates to that segment. You're going to use that theorem in a moment. The next thing you're going to do, once you have connected D to E, is you're going to find that there are these two triangles formed on the inside of our larger triangle. We have this triangle AFC and this triangle DFE. You're going to prove that those two triangles are similar to each other. So yes, similarity is a key to this theorem. So you're going to prove that those two triangles are similar. And last hint, okay, so first hint is, connect D to E. Second hint is you've got yourself similar triangles there by a special type of segment that you know DE to be. And then the last hint that I'm going to give you is using, and I'm going to write this down for you, you're going to use the lemma proportion entailment A. Let me remind you what that one did. The lemma states this, that if you know a proportion to be true, A over B is equal to C over D, then what you're allowed to do with this is you are allowed to add the numerator value to your denominator value. So keep that in mind going forward with the triangle medians theorem. And again, I'm going to leave this for you to figure out on your own, of course, with the several hints that I give you along the way. There's a phenomenal theorem we're going to conclude the worksheet with, which is known as the angle bisector theorem. Let me explain what happens with the angle bisector theorem. So we're given any triangle, ABC, and again, any triangle. Doesn't matter what this triangle is, equilateral, isosceles, scalene, whatever it may be, it's just an average, ordinary Joe Mama triangle, triangle ABC. If we bisect an angle in that triangle, as it turns out, it cuts out some proportional parts within our triangle. Here's what unfolds with the angle bisector theorem. Notice that the segment BM, which is our angle bisector there, it cuts our third side of our triangle here into two parts, an AM and a CM. But there's also the two remaining sides of our triangle, AB and BC. As it turns out, those four parts of the triangle that's formed are in fact proportional. So here's what you're going to prove. It's the ratio of the two sides, BC to AB, so you ratio the two sides together, is actually the same ratio of the two parts of the third side, CM to AM. Now, the way I remember of how to set up this proportion is I think of this angle bisector as being kind of the divider. And what I'm doing is moving from one side of my divider to the other side. That's what I'm doing. I'm moving from one side to the other. So I'm saying the side would be BC to AB, and then I do the parts of the third side, CM to AM, and that's how I set up this proportion. And again, that's what you're going to prove on the worksheet. Now, before we get to the worksheet, though, I do want to kind of give you kind of lead into what's going to happen on this worksheet to prove the angle bisector theorem. What's going to happen is going to require a construction. Okay, so here's the suggested construction on proving the angle bisector theorem. Essentially, what we're going to do first is we are going to create a parallel ray. So from point A, I want you to create a parallel ray to the angle bisector, which means notice that BM is parallel to this parallel ray, AD, right? This ray AD. Well, then what we do is we take our side CB, okay, side CB, and we extend it through point B such that it intersects here our ray at point D, and we can truncate the rest of our ray off, thus forming this additional part to our diagram. Well, as it turns out, what we have strategically done is, if you notice, the entire triangle ADC, this entire triangle, it actually has a line parallel through it. What does that mean for us? Here's your hint. T, P, T, triangle proportionality theorem. That is one of the previous theorems we've seen in this chapter, and with the triangle proportionality theorem, we know it cuts that into some proportional parts. You're going to use those proportional parts then to set up that proportion we're looking for, specifically with the angle bisector theorem. Okay, so we've come to the end of our application lesson. The application worksheet is a long one. Make sure you start that one immediately. There's a lot to it, a lot of application in terms of proof and also just application in terms of some problems. If you do come across any questions on that worksheet, do not hesitate to email. I'll get back to you and help you with your questions. With that, be good and do good.